Today we saw how the CDF method can be used in a very simple example to determine the distribution of the output random variable y. So, the goal in all of this is to find the distribution of y, whether it's as a CDF or a PDF, it does not matter, right. So, today we are going to cover this or talk about this PDF method, for which of course the assumption is that the y does have a well behaved PDF, is not it. So, what are the conditions for this? Well, x should, so the conditions are, we will write them down so that there is no doubt about this, x should be purely continuous, right. Then G should not have flat segments. G should be reasonably well behaved also. You do not want to take some crazy G, but let us say we are not interested in looking at totally crazy G which jumps up and down arbitrarily, right. We are going to rule those kinds of things out. Say for so the main constraint on G is that it should not have flat portions in omega x, should not be because this is obviously something which is allowed in practice and so we have to write it down separately, right. So, if these two conditions are satisfied, then this Fy will be properly definable and computable also, and we can look at how we might want to get it directly instead of going through the CDF route, isn't it. As usual, we are going to make use of the conservation of probability principle to find this. Anyway, the first step anyway you have to find omega, right, omega y. This you cannot do without, as I emphasized yesterday. And then the second step is to find the density function for all y in omega y, point wise. In other words, you are finding this output PDF point by point, but there could be an uncountable infinity of points here, but if you if you just take it for an arbitrary y in omega y, and if you can find it as a function of y, then you have solved the problem, isn't it. But that does not take away the fact that you are actually defining it point wise. And what is interesting here is that there could be a small number of points for which you cannot find Fy because of reasons that will become clear as we take up some examples, right. So, for some points in omega y, you may not be able to find one unique value of the PDF, but such points do not matter, right. When you have a function, it does not matter if one or two points you cannot specify it exactly, like for example if you take the unit step, it does not matter if you define u of 0 as 1 or half or 0, does not it. In most cases, in no case that I can think of, right, you need to worry about what its exact value is at 0. You can define it to be whatever you want as per convenience. Like that, here also there will be one or two points where you might, right, account a small, you might even say a finite number of points where it is not possible to exactly determine it using this procedure that we are going to list out right now, but that is okay. Okay. So, what we are going to do is take the general case, I mean general in the sense I am not going to, I am just going to take some arbitrary G which is, right. So, let me say that this is the origin, this is y equal to g of y, let me just say y, and this is y equal to g of x, and this is a function g which is not necessarily monotonically increasing or decreasing, but can go up and down. Okay, and let us say that for the sake of argument, right, that we have omega x maybe between here and here. Just So that I want me, or maybe I should take this, okay. Let me take this point above this, just so that I have some variation. Right? Of course, you're free to assume that omega x is goes on forever, but then I have not drawn g in that fashion, so I'm limiting the right omega x to the portion where I have drawn the g, isn't it? I don't want to get myself into trouble by saying omega x goes on like this and I have not defined g beyond this. Anyway, so let us focus just on this simple case where this is a finite interval and this is the g in that interval. Right. So what is omega y? Omega y is obviously the widest interval of values that you get on y, and it's for the non-monotonic case it's not so simple, right? You have to go and look at the variation of the function in conjunction with omega x and see. So here we might say that this is the smallest value and this might be the largest value, just this particular case. So this is the omega y. Let me write it like that. The set of values taken by y is from here to here. Okay. So now if I pick some value small y in that interval omega y, which corresponds to drawing a straight line like that. So I am interested in the event that consider, let me start here, consider this event y small y less than capital Y less than y plus dy for some small dy greater than 0. So always in these things this dy is larger than 0 and it is much smaller than 1. Right? It is the typical calculus differential, right? Positive differential. So that is an event which says that I am looking at these two horizontal lines and I am looking at the probability or rather the event that the output is in that interval. So what do I want to do with this interval? I want to map it back into x. So I want to look at what values x should take so that y takes values in the interval y to y plus dy. It's as simple as that. And if I map this all I have to say is the probability of this is obtainable from the description on x somehow, which is not too difficult to do because it turns out that if I have, let us say, if I take y, not y plus dy, if I take y and I have, how many roots can I find here? So this is a root, this is a root, x1, x2, unfortunately this omega x is come in the way, but I think I can write it without too much clutter, x1, x2, x3. I have 3 roots for this particular value of y. So if I take y in omega y, obviously it has to have at least one root by definition, otherwise there's something wrong with omega y, isn't it? So let x1, x2, x3, of course it can be more, but let me say for the time being that we have 3 roots. That is all the 3 roots, right? The 3 roots of what equation? This gx equal to y. The 3 real roots where all of these xi has to belong to omega x. You are not interested in roots of the equation outside omega x. Right? There has to be at least one, but to obviously to make it more general I am assuming more than one, and in this picture there is 3. So now what variation should x have so that y is between capital Y is between y and small y and y plus dy. The variations in x can be written as a union of disjoint events, mutually exclusive events, which are what? If I want to be here, then the input should be what? It should be either here or here or here, and the three events in the input side are mutually exclusive. So, the key point in this as far as this picture is concerned is, which this implies, I suppose I can start writing it here. There is, so we need, in this case, x1 smaller than, and I am assuming that g is decreasing at x2 but increasing at x1 and x3, so that I have x1 and I have here I need to write dx1, dx2, dx3, but if I start marking that here it becomes too messy, so let me not mark it, right. I just highlight it with some chalk here, and you know what I mean when I write dx1, dx2, dx3. Now of course you can't assume that all three are okay, let me write it in this with respect to this particular diagram. I am going to write, okay, I will write it like this, or I will write x2 minus dx2 to keep dx2 positive, because the function is decreasing at x2. This is right. After all, you know the function, you might, there is no loss of generality in saying I look at the function and see what sign I have to give for the dx at that point. So one of these three events has to happen for this to happen, and these are all ME. In other words, if x is going to sit in this interval, it cannot at the same time sit here and sit here, right. Disjoint intervals are always ME, basic fundamental property, right, disjoint intervals, right. So therefore, what does conservation of probability say in this case? The probability of that is going to be exactly equal to what? The sum of these three. Well, let me write this as A1 plus, so I will call this as A1 rather than keep writing it all over again. So I have three events here, I have A1 plus A2 plus A3. This is the most important equation that we need. This is, again, let me right, this is conservation of probability. If you do this properly for all the points y, you are guaranteed that the unit probability in x is going to be transferred to unit probability in y. So you should not leave out any of the output points or output intervals. All output intervals that can be mapped via G should be accounted for. Why is it now easy to, or supposing you make dy very small, right, and we are assuming that G is well behaved, right, and it, in that so the assumption we make is that G is a smooth curve, so that as dy goes to 0, all the dxi also go to 0, right. So G, we are going to impose some smoothness condition on G also, right, so that we can make that statement. So if dy is small, dxi are also going to be small, and each of these, the first order approximation, say how do you write these p of a1, p of a2 and so on. So it turns out that this p of a1, for example, is what, if for small dx1? Right. So it is a density function at x1, fx at x1 multiplied by dx1. Now dx1 is positive, but all these dx's are positive, that is another reason why, right, we want to keep them that way. I cannot write if I am allowed this dx to have sign, then I have to worry about is it going to be positive or negative. So I have written it so that it is all positive. So what about P of A2? Similarly, likewise this is, so this is x2 into d, again dx2 is positive, and it does not matter whether in the interval it is to the left of x2 or to the right of x2. If dx2 is small enough, it is the same. Then P of A3 will be fx of x3 dx3. Now note that however the magnitudes of dx1, dx2, dx3 can all be different. Why? Because the slopes can be different. There is no reason that this slope is the same as here. It may look the same. See, it is difficult to draw and make the slopes look very different. The eyes especially are, or maybe I drew this too much like a sine wave, right? So maybe you should draw it with some highly asymmetric kind of rising and falling, so you can see for yourselves that even in a rough diagram you can see that dx1 cannot be the same as dx2 in general. What about the left hand side? The left hand side by the definition of the density function is just the density of y at y of capital Y at small y, or the density of capital Y at small y multiplied by dy. Dy we have assumed to be some positive quantity, small positive quantity to begin with. So what happens? I am just writing equals here. This equals is only right when, let me say for small, I will qualify it, for very small dy, which implies small dxi. So what do we have here? Here I have 3, I know I have 3 roots, I am writing it as 3, right. So here dxi is all, wait, let me see, and dy is strictly positive, not 0. So I can divide by dy and get a formula for the output density that I want. So this is going to be, I will just write sigma over I. I has at least 1, but some number, in general more than 1. What is this quantity? From your favorite calculus class of whenever it was. It is the derivative in 1 by the reciprocal derivative at xi. Not only that, it is a magnitude of the derivative. I do not care about the sign, I only care about the magnitude, right. I only care about the magnitude derivative, not the sign. So it is written like this, right, 1 by g prime xi. Why does this derivative come into the picture? It comes into the picture because you have fundamentally continuous quantities, and if the derivative is large, that means a small variation here can produce a much larger variation here. Conversely, if the derivative is small, right, you need a larger variation here to get a smaller variation here. So that is why unlike in the discrete case, in the continuous case you are dealing with intervals, and when you are dealing with intervals and functions, there is no escaping some calculus. But we have had this kind of business calculus, I mean computations ever since Newton right, wrote on differential calculus. So, there should not be any problem for us, right, and therefore, we will write this as sigma over I fx of xi divided by mod of g dash, the derivative at xi. This is basically the formula we want, and we are going to assume of course that the derivative is not 0. That is, in other words, if you have the 0 derivative, this is what I was alluding to earlier, you cannot really directly apply this formula. That is, if you go out here and say where is a local maximum of g, at that point it's not, you cannot easily map some dy to any dx. First of all, the first order maths that the models that we have done here may say that dy has to be 0 at a maximum of g. It does not even actually make sense to give a variation dy, right, when you have hitting a maximum or minimum. So, but if you have only a finite number of such maxima and minima, it does not matter. You do not have to calculate fy, you can say fy, I do not want to define it at those finite at the small number of points at which g has a local maximum or minimum or local extremum. So this g, you want this to be, this magnitude derivative to be strictly larger than 0. For this computation to work, right, g prime xi has to be positive, more magnitude. So, if equals 0, i.e. local extremum max or min of g, what happens if then this method, then fy cannot be found using this method, right, this way. Actually, it turns out in many situations, that is, this equation does not make sense, is what I am writing here. In many situations, it turns out that such local maxima and minimum of g actually result in the density function going out to infinity, which we already have one example of, right. We did one example when we talked about that arc sine PDF. We will come back to this here again, that 1 by square root of pi into 1 minus root 1 x squared or something, that is going to come as a result of a transformation or a function of, right. But again, let me not, just for your the camera and for your notes, this is not an issue, I repeat, when there is only a finite number of such points to worry about. And we have ruled out, or we have said, this method anyway will not work if there is a flat portion. If there is a flat portion, then there is an infinite number of such points in some sense, right. There is an infinite number of rows, uncountable infinite, supposing g is flat somewhere, then you are not supposed to use this method anyway. Fy in fact will not have a good meaning. So therefore, since we have anyway started off assuming that there is no such case, you can say safely there is only going to be a finite number of maxima and minima, and therefore it does not matter if you do not find Fy at such points. Okay.